The kinetic molecular theory, or KMT, what it's talking about can easily be seen in the name. Kinetic has to do with motion, how things are moving, molecular, molecules, and theory. So it's a theory of how molecules move. The kinetic molecular theory applies to solids, liquids, and gases generally, but today we're only going to deal with the gases part. Today, in this lesson, we're dealing with the kinetic molecular theory of gases only. Now notice that I have two S's in my word gases there, and that's a story for another day. So, one of the things that we assume about gases is that they are ideal gases, and which means that they're going to follow these assumptions. The following assumptions we make for ideal gases, these are assumptions that a theory makes that helps us describe what things are going to do. First thing that we assume is that the speed of the gases is proportional to temperature. In other words, as the temperature goes up, the average speed of the molecules in the gas goes up. That's what we mean by proportional. If things are proportional, as one goes up, the other goes up, if they're directly proportional. We'll get into direct and inverse proportionality later, but for now we just know that speed and temperature go together. Hotter things move faster. Second assumption we make is that all collisions between molecules are elastic. There's no energy loss. They don't slow down because they hit one another. They travel in straight lines. They're mostly not affected by gravitational forces and things like that. And that they're point masses. In other words, the gas molecules themselves have mass, but they don't really take up any space. So that's what we mean by point. They have no volume. Now, each of these assumptions that I've circled is actually not true, but they're very, 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 very close to true. They're just barely false. There's only tiny little bits wrong with it. And so it's going to work at normal temperatures and pressures. So collisions, tiny little bits of energy are lost in collisions. They do slightly bend. They do take up a little bit of space, the molecules themselves, but they're so incredibly small. They're going so incredibly fast. They're so very close to elastic that these assumptions work for most of the time. Well, when don't these assumptions work? These assumptions don't work whenever these assumptions don't work whenever the situation exacerbates these differences, these problems. And when is this? Well, doesn't work. The ideal gas assumption doesn't work at very large temperatures. Pressures I meant to say. Does not work at very high pressures, and it also doesn't work at low temperatures. The reason it doesn't work at low temperatures is because at low temperatures things tend to condense into gases tend to condense into liquids, and obviously assumptions you make about gases would not apply to liquids anymore. So that's that. So as we go through the kinetic molecular theory, we're going to refer constantly to this visual example. It's a website. You can write down the URL there. I'm going to click in here and it's going to open up this window. This is the kinetic molecular theory of gases applet that was listed at that site. There's a description we can look at, blah 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 blah, yada yada, and then whenever I hit play, what's going to happen is that these gases are going to begin to obey the ideal gas law assumptions and start behaving like ideal gases. And so let's see the different things that this model can do. So things that we can keep track of as we look through our model. First of all is temperature. If we go back here, the temperature is something we can control, and we learned from our assumptions that higher temperatures should move faster, and therefore we click that, we see that the average speed of the molecule does change, and so we can play around with that. The next thing we can look at is volume. We can actually change the volume here with this little drag arrow. We can make things smaller. We can make the size of the box, not of the molecules, but of the box. We can change the size of the box that they're in with that. The next thing that we can adjust with this little applet is the number of gas particles. We can make it either have a lot or not very many. So we have these little blue spheres, these little blue balls bouncing around in here, and we can change it from 30 to 20 to 10. And so That's another thing that we can control. We can also pause it anytime we want or hit play again. So we can mess with all of those different things. And so what we're going to do here, and there's one more, we're going to look at pressure. Pressure is kind of interesting because we actually can't really adjust pressure directly. The website will let us change each of these things directly except pressure. However, pressure is something that we can picture. Picture this. Whenever you see these balls bouncing around, count how often the balls hit the side of a box. So right now there are not very many times that a ball hits the side of a box. But if we go in and we change different things, we can see that the number of times that the ball hits the inside of the box goes up quite a bit. The pressure goes up quite a bit. So collisions of these blue balls with the sides of the container are what we mean whenever we think of pressure. And so here's what we want to do with this. I want you to think about these kinds of things. So we have this simulation and we can think about these questions. P is pressure, V is volume, T is temperature, and N is moles of gas, or how many particles we have. And so I want to think about these questions, and you can play around with these on the model. You can go there yourself and try these. Questions like, what happens to the pressure when you make the temperature bigger but don't change the volume? What happens to the pressure when you make the volume smaller but don't change the temperature? What happens to the pressure when the number of moles, number of particles gets bigger but you don't change anything else? What happens to those? Is that predictable? Can you kind of predict what's going to happen? Can you look? And some other questions. What if the box were stretchable? In other words, if doing things would allow the box to change its size. What would happen to the volume if you increase the temperature, if it were elastic? Would it go bigger, smaller? Would it be no change? What about what would happen to the volume if you changed the number of particles in there? If you made more particles, would the volume go up, go down, be no change at all? What would happen there? And so these are the kinds of questions that we can ask. And if you can understand all these in the applet and you can look at the website and make the correct predictions there, then you have a pretty good idea of how ideal gases behave. And what all this is going to lead to us is the gas laws. So this chapter, the biggest thing that we're going to be doing is we're going to be learning all sorts of different gas laws, the behavior of gases. And it's a series of descriptions of when you change one thing about a gas, its pressure, its temperature, that's going to change some other thing about the gas. And the gas laws directly tell you what those things are going to be and how they're going to change whenever you do that. It's what this chapter is all about.